It's my real pleasure to have today introduce Man-Hui Lee, who is visiting us from the University of Hong Kong. Man-Hui Lee is a very well-known dynamicist. He was at CITA some time ago.
Long time ago.
After being a citizen, he held temporary positions at the University of California, Santa Barbara.
And Queen's University.
And he's now at the University of Hong Kong. He will tell us about some weird systems in binary string dynamics. Okay.
Yeah. Well, thank you. It's always a pleasure to be back here. I don't know, 13th floor, I think it used to be the astronomy department, right? Yeah.
Exactly.
Yeah. So used to hang out around this room probably. Today I'll tell you a little bit about some work that I've been doing about the dynamics of circumstellar planets in binary star systems. So this is work done in collaboration with a few people. Trifon Trifonov, he's right now in Max Planck. He was a postdoc with me for a while. Also with a student of mine, Kaho Wong, and a current postdoc, Zhang Xiaojia, who's, so these are people at the University of Hong Kong. As you will see, the work kind of started with people at University of Heidelberg, particularly Sabine Riefert and Andreas Kornbach. These are observers that have been, they started a program looking at giant stars, radial velocity measurements of giant stars. And so the systems I'll be telling you about are primarily from that, started from observation from that project. So I'll give you a brief reminder about some of the basic things about search for extrasolar planets, and then I'll move on specifically to talking about planets around binary stars. So as most of you know, the first extrasolar planet around a sunlight star other than the sun was found in 1995. And in the last 23 years, we now have over 2,800 confirmed extrasolar planetary systems. And at least 600 of these are known to have more than one planet. There are multiple planet systems. And probably more of the supposed more of the planet systems that have only one known planet. Most likely they have more than, they also have multiple planets. It's just that we haven't found them. If you know anything about extrasolar planet discovery history, you know that most of these were discovered by two methods. One is radial velocity method, and the other one is transit. So I'll just briefly remind everyone what these methods are. The first one, radial velocity method, is an indirect method where you are actually measuring the motion of the star around the center of mass when there's a planet going around that star, right? And so you're using, you're looking at the light from the star, and measure this, the spectrum of the light and monitor the Doppler shift of the lines in the spectrum. And if you see periodic shifting back and forth due to Doppler shift, then that's most likely due to the presence of a planet causing the star going around periodically around the center of mass. Of course, it's more complicated with multiple planet systems. When you have radial velocity measurements, then when you see periodic radial velocity curves, then from the shape of the radial velocity curve, you can actually infer the eccentricity of the orbit of the planet. If you know the mass of the star, then from the orbital period, of course, that means you can infer the semi-major axis, the size of the orbit from Kepler's third law. And the total amplitude of that radial velocity curve gives you the minimum mass of the planet, because you cannot break the degeneracy of the mass of a planet times the sine of the inclination of the orbit. Unless you have a multiple planet systems, and you can actually detect the interaction between the planets. In that case, there's you can actually break the degeneracy of this mass of the planets times the sine of the inclination. As I said, the first planet was in fact discovered by this method, radial velocity method, back in 1995 around the star 51 Pegasi. And so again, from the amplitude, that gives you that the minimum mass of the planet is about half Jupiter mass. That's not unusual. Of course, what was really unusual was the orbital period that turns out to be 4 days. So this is a Jupiter mass planet going around the star every 4 days. And so basically from the very first planet, the extrasolar planet discovered, we already know that there must be a large variety of other planetary systems with very different properties from the one we are living in. The other method, transit method, conceptually is easy. What you're doing is you monitor how bright the star is. And if you're a planet going around that star and the orbit happens to be nearly edge-on, then every time that the planet goes around the star, for a period of time, it would be going in front of the star and blocking out some of the light from the star. And so that caused the brightness of the star to dim a little bit. And the amount of dimming is basically roughly proportional to the ratio of the area of the disk of the planet versus the disk of the star. So that from that, you can then infer the size of the planet if you know about the radius of the planet, if you know about the radius of the star. But again, of course, this is not something that will allow you to discover most planetary systems because this was only, you can only see transit if the orbits are nearly edge-on to your line of sight, right? And so the amount of dimming, of course, depends on the size of the planet. It's roughly about 10% if you're talking about Jupiter-sized planet. But if you're trying to find Earth-sized planet, then you're talking about something like 1 part in 10,000 change in brightness. And so that was the incentive to, of course, send one of the most successful missions for extrasolar planet search, Kepler. And with Kepler, we've now discovered thousands of planetary candidates, and many of these are confirmed planets. And you can see this interesting distribution where actually I guess the peak in the number of planets are actually in Neptune-sized planets. They also, of course, discover a lot of Earth-sized planets. And then there's kind of a drop into the Jupiter-sized planets. So if you look at all of the confirmed planetary candidates, right, and plot some of their basic orbital properties and mass, so on the left, you see the orbital periods in logarithmic units versus the minimum mass in units of Jupiter mass. All right, and over here is orbital period versus the orbital eccentricity. Then you notice that, so the hot Jupiters are the objects that are here, right? The orbits, the planets that have Jupiter mass and orbits that are of order a few days. And actually, there are now ones below 1 day, and whatever, the record is half a day down here. There are also some Earth-sized planets and super-Earth planets down here. There seems to be some sort of a gap here in terms of the planets that are very close in. And then there's a whole lot of planets that are kind of large planets out at large orbital distances or periods from the central stars. Of course, the empty space here is primarily due to all the observational selection effects. It's not the fact that there are no planets there. At least we don't know. The other surprising thing, again, of course, is that for when you look at the orbital eccentricities, unlike the planets in the solar system that are mostly nearly circular orbits, there are actually a lot of planets that have highly eccentric orbits. And the record is something 0.9 something. So it's a very eccentric orbit. Right? So by now, as I said, we have of order close to 3,000 confirmed planetary systems with at least 600 of these have multiple planets. And we now, as you saw from those diagrams, there are many different types of systems. You have these so-called hot Jupiters, Jupiter-sized planets that are very close to the stars. You have planets that have very eccentric orbits. And also, I haven't said much, but there are also these planetary systems, multiple planet systems, where you see planets that are actually in or near mean motion resonances. So that, in the simple term, that means that their orbital periods have simple integer ratios, like 2 to 1 or 3 to 2. But up to this point, I guess, so we actually know, of course, from this, we already know a lot about planetary system around other stars. But there are at least a couple of areas where there's still not a lot of discovery, and I'm sure we really don't know in full perspective what their properties are. One is actually about planets around giant stars. All right, so why giant stars is, so if you know anything about the survey for radial velocity method looking for planets, they were primarily focused on F, G, and K stars in the main sequence. And the reason has to do with you need enough spectral lines to be able to do the radial velocity method accurately. So if you go to higher mass stars on main sequence, it's very difficult. And so to actually know more about planets around higher mass stars, you actually have to look at them when they're in giant phase. And so there was an incentive then for doing some survey of giant stars so that we know more about the occurrence and properties of planets around more massive stars. The other one that we also know very little until really recently. I'm sorry.
First off, so there's some detection of contamination around white dwarfs. Can you use this information to infer about the population of planets around giants?
You probably could, but I think we do not have that many examples of, yeah. So that is, yeah. So the number of known, I guess I'm not even sure, are there any confirmed examples? Probably not, right? Yeah. Yeah. So, but there are in fact many good examples of planets around giant stars. So that's, so I don't know if there's a problem of not finding any around white dwarfs, despite, I guess there's been actually quite a few efforts looking for those. Yeah. The other problem is actually about planets in binary star systems. Of course, as most of you know, most stars in the galaxy are not singles, right? So it's actually important to know something about the occurrence of planets around binary stars and how they may be similar or different from their occurrence in single star systems. So the examples, the main topic I'll be talking about actually touch on both of these because it's actually the particular system I'll be talking about is actually coming from a survey of giant stars, but that also turned out to be a binary star system. Right? So the particular survey that where the observation come from that I'll be talking about is from this Lake G and K giant star survey from that's using radial velocity method. So again, this was something started by Sabine Riefert and Andreas Kornbach back in 1999. They actually finished observing in 2012 because I think it was the iodine cell that actually broke and it was never replaced. So there was something like 12, 13 years of data in total. The radial velocity precision that they achieved was around 5 to 8 meters per second. And that is sufficient for giant stars because giant stars actually are intrinsically quite noisy. So even if you have better radial velocity precision, it's most likely not going to help you. So there's been a steady output of systems that have been, so out of this sample about 370 stars, they have discovered at least 70 stars that have planetary systems and at least 18 more candidates. I'm not even sure I have the right total number or which is in which category right now. But it's roughly 30-something or to 40 systems in total that have already confirmed or suspected planets. The other thing that is a bit problematic, again, as I say, giant stars can be actually quite noisy in radial velocity. Then there might be other things going on with the stars. So one of the things that is useful is to be able to actually confirm that you're seeing the same radial velocity periodic signal in some other wavelength. So that was actually done for some of the stars in the infrared. So some of the stars in that sample with suspected planets was also observed with a near-infrared spectrograph. That was on VLT, so and to see if it was seeing consistently the same periodic signal with the same amplitude.
What's the minimum effective temperature that the survey goes?
I'm not sure. I have to check. I'll have to check.
Well, the gist of the question is how big are the giants that have
So these are, I think the stars that I'm telling you about, I think they are on the order of 10 or less than 20 solar radius.
My impression is that radial velocity would still be difficult for a Jupiter mass planet around accelerated the giant branches.
So these are not in that state. Yeah, these are not in that state. They're like in the, I think they're usually in the horizontal branch or AGB. Yeah. So there's the observational aspect, and where I got involved was, I think, when Andreas was, I was talking to him, and they already have some suspected multiple planet system, and he was asking me if I was interested in being involved. So then the analysis that we were doing then actually was fitting the radial velocity observations that they have, doing primarily, so we do different things, but we do dynamical fits. What that means is that we are actually fitting, including the dynamical interactions between the planets, so we don't assume that they're just on independent Keplerian orbits. And so that's using chi-square minimization. We sometimes do the systematic search through parameter space so that we get a better sense of the different possible solution to the radial velocity data. Because sometimes you actually, one of the problem here is that whatever the best fit that you find from chi-square minimization may turn out to be not dynamically stable. And then you have to ask, how far do you have to go away from that best fit to actually find stable solutions? And so sometimes it's useful to do a systematic search in parameter space. Other times you can do that just by doing some sort of distribution of fits, doing something like bootstrap method or MCMC. And combined again with the fitting is to test dynamical stability so that whatever the fit that you come up with is actually stable on the time scale of interest. So these were done mostly with some sort of symplectic integrator. So before I talk about the binary star systems, I'll give you one example of a really interesting system that was discovered by this survey. And it's around a star called New Ophiuchi. And actually, this turned out to be not about two planets, but rather two brown dwarfs that was discovered around this star. So this star is a horizontal branch star that has a mass of 2.7 solar mass. There were, the LIC survey collected 150 measurements. A Japanese group turned out to be they were also doing a giant star survey. It was also in their sample. So they had 44 observations. There was infrared observations that got the same, that was consistent with the optical observations. Okay, so this is the radial velocity curve. I think the light blue points are all the LIC data points, and the green ones are the Okayama Japanese data. Okay, so it's really clear. So that you see two periodic signal here. There's the shorter period one, and then you have an overall longer period. When you fit the data, you find that you have two planets that have minimum, well, this is edge-on fit. So the minimum mass basically would be 22 Jupiter mass and 25 Jupiter mass. So these would be in the brown dwarf range. But what's really interesting is the periods are 530 days and 3,180 days. If you take the division, it gives you almost exactly 6:1. Okay, so if you then analyze the dynamics of this system, this is what you get. So this is showing you the evolution of the semi-major axis, eccentricity. And these 6 angles here are the 6 angles associated with the 6:1 mean motion resonance between the two orbits. Okay? And what you see here is that all of them are oscillating around 0 degree. So that tells you that this is a system where the two brown dwarfs are clearly in a 6:1 resonance with all of the resonant angles librating. And the fact that these are all going around 0 degree tells you that the two orbits are, on average, aligned with each other. Okay? And we have checked this for again, this is the best fit, but so here you can, again, do whatever the parameter search or MCMC or bootstrap. You can see, and what we found is that basically all possible reasonable fits to this system would give you a 6:1 resonance. Okay. So as far as I know, I think this is the highest order resonance known in any system. There's another one that's in 5:1. And I think that one is also pretty secure.
The mass ratio is pretty high, right?
That one is actually a brown dwarf inside and the planet on the outside in a 5:1 resonance. Here is actually two brown dwarfs in the 6:1. Yeah.
Mass ratio is
I don't think it was that extreme. You mean this one? No, this is 1 to 1. It's 2.
No,
20.
the mass ratio to the star.
Oh, to the star.
Meaning the resonance is very wide.
So the star is 2.7, so it's 1%, right?
Yeah, it's 1%.
Yeah, 1% of the cell.
Yeah, but the eccentricity is also pretty good.
The eccentricity is high, yeah. Yeah.
So it's EQ.
Yeah. So if you assume that they have non-trivial eccentricity, it's easy to get captured into the 6 to 1. If they're initially circular, it's very difficult. Yeah. Yeah, so we've also done some calculation trying to figure out what you need to get captured into that resonance. Yeah. Yeah. So this one is actually, at least observationally, is actually a pretty clean system. It really looked like it's a nice 6 to 1 example. So then the other system that I got involved in was actually about planets in binary star systems. So just to remind everyone, when you have a binary star going around each other, then of course you can have two types of planets. You have the ones that go around the binary stars. So these are called circumbinary planets, and technical, I guess for dynamicists, these are called P-type planets according to the Vorax classification. And then you can have the situation where the planet is going around one of the stars. So these would be circumstellar planets in binary star systems, and these are called S-types. Okay? So I won't say very much about the circumbinary one, but of course their discovery have been most successful again with Kepler. There are now, I think about a dozen of these or so. Again, mostly discovered by Kepler, at least the really firm examples. But for circumstellar planets in binary star systems, there has been kind of a long history of some claims that are real, some claims that are not real. And it kind of depends on how widely separated the binary is. So here's a plot showing you all of the known circumstellar planets. So on the x-axis is the binary separation in AU. Some of these are just whatever they observe. They're actually observed on the sky to be a binary. So it's just whatever the apparent separation is. Others have actual orbital solutions. So in that case, it would be the semi-major axis of the binary. On the y-axis is the semi-major axis of the planet, both in AU. So this is the 1 to 1 line. So on this diagram, the example that I'll be telling you about are in fact the two with the closest binary separation. So it's this one and that one. Okay? So one of these is, the main focus is on this one, HD 59666. And the bar here is in fact telling you about the periastron and apastron separation. So this is a very eccentric binary. York Tantus is the other one. It's not so eccentric, but it's really close, the separation. So both of these have suspected planets. So HD 59666 is the primary star is a 1.9 solar mass star. There were 88 radial velocity observations from the Lake survey with precision of around 5 to 6 meters per second. Again, there was infrared observations to confirm that there was the same variation in the infrared. So this is the radial velocity over the Lake survey. So the blue points, again, are all the Lake survey data. The red are the infrared data. Okay, so very nicely, you can see very systematically that you have this periodic short period variation over the entire time. And then you have this big variation due to the binary motion. Okay. So in the observation, they haven't in fact seen one orbit of the binary. But because the orbit is so eccentric, and you see the periastron passage, then you actually do not need to see through the entire period to actually get the binary orbital period accurately. So if you do the radial velocity fitting, you find that the binary companion is a half solar mass star. Well, the minimum mass is half solar mass. It has a semi-major axis of 13.6 AU. But of course, when you see a curve like that, you already know that the orbital eccentricity is really large. So it's 0.73. It's a very eccentric binary. The planet is 7 Jupiter mass, minimum mass. It has a semi-major axis, about 1.1 AU. And the orbit is fairly circular, 0.05. Okay? So if you start to estimate whether this could be possibly a stable orbit, you start to worry, okay? Because if you ask, how far apart, when the binary companion is at periastron at the closest point, how far away is it from the planet? And it turns out that the separation is only about 1.5 Hill radii. And this is if you use the periastron distance as the distance here, rather than usually using the semi-major axis. Okay? And also, if you use the classic result from Holman and Wiegert, asking what the critical semi-major axis is for a planet in this system, you find that the observed planet is actually outside the critical semi-major axis, just outside, which implies that it should be unstable, according to this Holman and Wiegert criterion. So you can then check if that's going to be the case, and indeed, if you take whatever the best fit solution to the radial velocity curve, and you assume that the orbit are coplanar and the planet orbit is going in the same way as the binary, then you find that, in fact, this system is not stable over timescales of tens of thousands of years. Yeah. That's not good, right? Because the system actually has been around for a long time. Okay. So you can then, so of course, again, the emphasis here is not to look at the best fit only. You really need to look at the whole distribution of all possible fits to the solution. And we did that. So here's an example coming from the bootstrap analysis. The light blue points are all the fits that turn out to be unstable dynamically. So most fits are not stable, just like the best fit. But there are a few percent of fits that are the red points, and they turn out to be stable. Okay? And so these are on the different parameters. I can maybe point to this one is probably the most interesting one. So this is the period of the planet versus the period of the binary. And these are the ratios of 40:1 period ratio, 39:1, 38:1. And you see that there are red points that are kind of in between the integer ratios. Okay? So that's a hint of something interesting about the dynamics. Okay? And indeed, if you integrate one of these red points and see what's going on with them, they are actually stabilized by particularly something called secular apsidal alignment. So this is the angle between the orbit of the binary and the planet. And you see that it's oscillated around 0 degree. And so these are fits where the planet orbit is nearly aligned with the orbit of the binary. And they stay that way through over the timescale of the secular evolution. Okay? And so you can see because of this alignment, there's actually very little variation in the planet eccentricity. And that keeps the system happy. Okay? And you can also see here the period ratio in this particular case is staying in between the 39:1 and 40:1, so it's something average is close to something like 39.4. Okay? So if you have an orbit that has the right eccentricity and starting with nearly aligned orbit, then if you're not near mean motion resonance, it is possible to be stable in this system. Okay? And alternatively, we also ask, what happened if you actually put the planet on a retrograde orbit, meaning that it's going in the opposite direction compared to the way the binary is going around. Okay? In that case, it turns out that the best fit for the retrograde orbit is actually slightly, only marginally better than the best prograde fit. Okay? So the best retrograde fit is about 1 sigma better than the best prograde fit. It is also, the other nice thing is that the best fit itself is already stable. Okay, so it's perfectly stable. The only thing you would notice here is that actually the eccentricity goes up and down by quite a lot. Okay, going up to something like 0.35. Currently it's down here. Okay. But again, if you look at the distribution of all different types of fits to the system, then now, unlike the prograde fits, almost all of the retrograde fits are dynamically stable on 10 million year time scale. And only very few are not stable, okay? So after we did this, so we wanted to know, what's going on with the dynamics in the system, right? When can you expect stable fits, and why are there these stable solutions that are in secular apsidal alignment? So then that was why my student, Gao Wang, he was actually, so this is actually from his master degree thesis work. So what he did was he actually treat the planet as a test particle and integrate orbits in this binary star system over 10 to the 5 binary periods, and then see, for different parameters of the planet orbit, so semi-major axis, eccentricity, different initial angles and different alignment angles, basically trying to figure out in what situation you can find stable orbits, right? So this is the sort of stability map that you find. So on the x-axis is the initial A of the planet, and the y-axis is the initial eccentricity. And basically the main thing is to focus on the really deep red points, which are the ones that are stable to the maximum time of the integration, okay? And what you notice are, well, so first of all, just to orient you, this is where the observed planet is. Okay, so it's about 1.09 AU, 0.05 eccentricity. If you take the stability criterion from Hohmann and Wiegert, what they defined was looking at circular orbit. What's the first point, as you go out, what's the first point you find unstable orbit? And in this system, it would be here. Okay, and it is consistent with what you get by looking at the equation from Hohmann and Wiegert. So it's about 0.98 AU. So it is indeed slightly outside. Okay? But what is interesting is here that you find instead of just what you would have expected, which is kind of a stable region that looks like this, right? So the more eccentric orbit should be less likely to be stable. So you might expect this region to be all stable. There are these isolated islands of stability. Okay? And so there are different things going on here. There are these stable islands, okay? And these are the ones that are actually stabilized by the secular apsidal alignment. But then you also see these things, right? And these are actually stabilized by mean motion resonances. And they are here, as you can see, very high order resonances, like 40 to 1, 42 to 1, 44 to 1. You don't see the odd numbers here, and that's only because of the initial conditions of this, for this particular test. So when we change the initial conditions, then you actually find the other set of mean motion resonances, 39 to 1, 41 to 1, 43 to 1, etc. Okay? So the ones that are stabilized by the secular apsidal alignment is basically just the same as the example I showed you already. Right? If you have the right eccentricity with the orbit initially aligned and between mean motion resonances, then those could be stable. Right? And then we also check for the mean motion resonances. Right? So here's a particular example of a planet that an orbit that is in 42 to 1 resonance. Okay? And you can see that some of the mean motion resonance angles are in fact librating. Also all around 0 degree. Okay, so basically there are two ways you can, beyond the classic stability region from the Hohmann and Wiegert criterion, there are two ways by which you can find stable solutions in the prograde case. So either in the secular apsidal alignment in between mean motion resonances, or if you're actually in the mean motion resonances. And if you then go to so this is for the prograde orbits. If you go to the retrograde orbit, this is the retrograde orbit. Then you find that actually the critical semi-major axis for circular orbits is actually at almost 1.5 AU, so the planet is actually down here. So it is well inside the standard stable region. And so that's why most of the retrograde fits are in fact stable. But if you do the same thing and extend beyond the critical semi-major axis, you actually see the same sort of behavior, that if you have the right eccentricity and initial angles, you can be either in secular apsidal alignment or stabilized by mean motion resonances. So I think that's what is new from this result, is that most people, I think they have not really seen this behavior before for planetary, circumstellar planet orbits in binary star systems. And I think the difference is because most people haven't actually looked at very eccentric binary orbits. And this only matters if you have very eccentric orbits. Okay. So this is for the HD 59666 system. The other system that actually was discovered earlier but somewhat controversial was York Tantus. Okay, so this was a system where the central star is 1.6 solar mass. Back in 2009, David Ram actually published a paper where he has a collection of 220 radial velocities that was collected on Mount St. John Observatory, which I think is in New Zealand. And the data, I think, the quality of the data is not the greatest, but you can see, obviously, you can see that there's a binary. So the binary signal is very clear. The somewhat controversial was the shorter period planet or signal, whether that's real or not. Okay? And the other interesting thing about this particular system is that the binary orbit is actually seen in Hipparcos data. And so they actually know the inclination of the binary, and it's about 71 degrees. So the data itself is a bit, the quality is not the greatest. And the thing that got people really worried whether this was a real system or not was actually, again, from dynamical stability. So if you look at, you can see that there are only maybe 2.5 orbits of the planet over one orbit of the binary. So the period ratio here is really low. Okay, so indeed, again, if you estimate how far apart are the stellar companion and the planet when the companion is at periastron, it is even more extreme than the other case. They're only separated by 0.7 Hill radius. So again, most likely not stable. And indeed, again, when you integrate the fit, it's very, very unstable. Okay? It's even worse than the other case. But, so this is actually, I guess, kind of going backward in history, is that then people actually then pointed out, there were a few papers where people found that, well, actually, if you put this orbit on a retrograde orbit, the planet, instead of being prograde, is actually retrograde, then it is actually perfectly stable. Okay, so you cannot rule out that, you cannot say that this is not a real planet just because of the fact that it's unstable, it's on a prograde orbit, because there are actually stable orbits. Okay? So more recently, so where I guess we've been involved in is actually more recently in 2016, David Ram actually published a much larger sample of radial velocity, almost 1,200. And I think overall the quality of the data is better than the one in the previous publication. So now you can see whatever, one, two, three, at least 4 orbits of the planet. Okay? And so the signal is now actually is also consistent with what he published before. So I think there's now it seems more likely that this is a real planet. Okay? And so if you, again, fit the radial velocity data, you find that the companion is, again, have a minimum mass around half a solar mass. It has a period of 1,050 days. The planet is 410 days. So again, the period ratio here is only about 2.5 or something like that. The binary is not as eccentric as the other case, so it's only about 0.25, but this is a much closer separation in semi-major axis. Again, the orbit of the planet is nearly circular. Okay? So again, if you test, and so based on the fitting to the latest data, if you again test whether a prograde orbit is stable, you find that it's completely ridiculous. It actually becomes unstable within a few years. And so there's no way for you to even fit this system if you try to do dynamical fit. It's just not even possible. So it's basically hopeless for putting this planet on a prograde orbit. Again, it is actually perfectly possible if you fit it with a retrograde orbit. So this is the best retrograde fit. And you can see that the eccentricity of the planet only goes up down like this. So this is on different time scales. So this is up to 10 million years. It looks perfectly stable. Okay. And again, if you check not just the best fit, but actually all the fits around the best fit, you will find that, so I guess the central plot here is the important one, showing you how up to what maximum time they're stable. So up to the maximum time integrated, this whole region is stable. Okay. So basically, if you, again, in this case, if you put it in a prograde orbit, there's just no solution at all. So it's even more extreme than the other case. You cannot find a stable prograde orbit. But if you put it in a retrograde orbit, it's actually over a wide range of parameters, it is actually stable.
So these are all 180 degrees inclination, or did you vary?
These are, I think, fixed with so the binary inclination is known.
Right.
So we've put it as so these would be, I think this particular diagram is for coplanar retrograde fit. We have tri-mutually inclined fits. I forget for this particular system how much you can vary that. But I think there's some leeway. So yeah. Because this, you can see here, is actually quite stable. Yeah. And we also didn't find, I think there are no, sorry, let me rephrase it. For this system, I think there are some isolated high mutual inclination fits. But there are not that, but there are no wide regions of stability. Yeah. Okay. So based on these results, I started to become interested in understanding what happened to, because we really don't know very much about the orientation of the planet's orbit in binary star systems. So I started to become interested in what happened, can you actually form planets in retrograde orbits in binary star systems? And so one of the things that my current postdoc is doing is actually trying to do some simulations comparing the behavior of proplanetary disks if you put them in prograde orbit around compared to the binary versus retrograde orbit. Okay? And so these are simulations done with the Fargo hydrodynamic code, again with either prograde or retrograde disks. The binary parameters we've been using are identical to the HD 59686 system, except that we vary the eccentricity of the binary, so we can see how things differ with different eccentricity. So some of the things are still ongoing, but I'll just show you a few results. Most interesting here is probably this plot about the size of the disk. And you can see for the prograde disk compared to the retrograde disk, the different colors are for different binary eccentricity. And you can see that generally the prograde disks are smaller in size compared to the retrograde disk. Okay? And this is at a particular time, but over time is basically the same. Okay? The other interesting thing is about how eccentric or how the eccentricity and the alignment of the disk is compared to the binary. So you can see here, so these are again examples of different binary eccentricity, 0.1, 0.2, 0.3. Okay, the red one is the retrograde disk, and the purple one here is the prograde disk.
Is this one location or is it here?
This is a disk average eccentricity. Yeah, so this is the weighted average eccentricity. And this is the weighted, so this is also weighted where the disk is pointing compared to the binary. Okay? And so you can see in all cases that this is in fact precessing. Okay, so it's actually, I guess, retrograde precessing. Okay? And there's some, so the disk always becomes eccentric. Right? That's not surprising. What is a bit unusual is actually for the retrograde case, instead, so in the prograde case, you kind of see that this become eccentric and kind of just flatten out and have some eccentricity. In the retrograde case, it actually have these up and down going on. And I don't have a movie, but from what we can see, has to do with, again, more violent interaction when you have a retrograde disk. When the binary comes into the retrograde into periastron, there can be actually more violent interaction between the disk and the binary companion. And then after that, it takes some time for things to build up again. And so then you have another episode of some instability going on. So it goes up and down like this. But you notice that at the bottom, it always goes down to some steady value for the eccentricity of the disk. Okay? And if you pay attention to how high the eccentricities are for the different cases, maybe not so more obvious in this plot, is, again, so here binary eccentricity 0.4, 0.5, 0.7. And you can see that for the retrograde case, that this eccentricity is actually staying roughly about 0.2 at the bottom. But in the prograde case, actually, as the binary become more eccentric, it becomes actually more circular, the disk. Okay. So this is kind of what's summarized here. So if you look at the time average disk eccentricity versus the binary eccentricity for the prograde case, it looks like the disk eccentricity becomes smaller as you have more eccentric binary. But in the retrograde case, it stays nearly constant.
Can you go to the previous?
Yeah.
So is that the last panel is showing that it's being lightweight in epsilon?
This one.
Yeah.
I'm not too sure because the orbit is because the binary, the disk is actually quite circular. So I'm not sure how reliable that is. Yeah. Okay, so I think that's the main point I want to come across with this particular stuff. Is unfortunately, this is still going on because we have some, it turns out to be quite complicated to try to get this done correctly in terms of how big a simulation region we need, etc.
What sort of shock patterns do you get in this binary eccentricities?
So that's something I need a movie to show you. Yeah. Is there some specific thing you? Yeah. So there's let's see. There's actually a stream of material that's coming. So we have a disk around this primary star, and there's actually a stream of material that go from that disk going into the secondary, especially during periastron passage. And so some of the material is shocked. Yeah.
Because I mean, in isolated disks,
Mm-hmm.
extra state strongly limited, isn't it?
Is what?
Extra state strongly limited and
Mm-hmm.
isolated
Yeah.
high ion disks
Yeah.
by shock. So I think that it's a very disk that are accessible. You're constantly driving the larger.
Right. Yeah. So here, obviously, the disk. So something is going on quite complicated with the interaction between the binary companion. Again, because especially for high eccentricity, it does come very close to the primary star. So the interaction between during periastron passage, the interaction between the secondary star and the disk is actually can be quite violent. Yeah. So that's why I was saying, here you see these episodes of things going up and down. And so when you see this peak here, there's some really violent behavior going on. Yeah. I should actually have a movie of this. Yeah. OK, so lastly, actually, just to advertise something. Let's see, is this the right? OK, I guess I put that at the end. Maybe I'll summarize first, and I'll talk about what the last thing is. Up to now, I guess what I've told you are actually primarily about these two systems, 59666 and York Tantus. And these are, again, the two binaries that are the closest separation that have known circumstellar planets. As you saw, for York Tantus, if you believe that there really is a planet there, the only possible solution is that it's actually on a retrograde orbit. And for 59666, there are two possibilities. It is possible to be prograde orbit, but in that case, it has to be stabilized by secular apsidal alignment. And as you saw in those stability diagrams, those stable regions are actually quite narrow. So how you form a planet ending up in that narrow stable region, not obvious to me. It could be if it's a retrograde orbit, then actually in some ways the life is easier because you're in a broadly stable region. But on the other hand, there's the problem that if you notice the eccentricity of the planet is going up and down by quite a lot. If I can find that plot. Right, so the eccentricity actually for retrograde fit actually goes up and down by quite a lot. And right now you're seeing it nearly circular. So it has to be, it would have to be a coincidence that you're seeing it right near when it's nearly circular. Right? Most of the time, it shouldn't be circular. So that's a little bit uncomfortable. So again, because of that, I started to ask myself, how you can actually form these circumstellar planets if they're actually in retrograde orbits. So I show you some work that we've been doing on trying to study retrograde circumplanetary disks. There have been other ideas, particularly someone have demonstrated, I think it's possible for circumbinary planets, if you have instability going on, that you can actually end up capturing one of the planet into an orbit around one of the stars, and it could actually be retrograde. Although I'm not sure you can easily end up with something that have a nearly circular orbit. So again, we'll have to see whether that's possible. The other thing that I didn't say anything about was actually the student Kao Wang. He also actually tried to generalize the critical semi-major axis that was done by Holman and Wiegert, but they did it for the prograde orbit. So he actually repeated the calculation for the retrograde orbit and look at how they differ or similarly from each other. Turns out to be quite simple. So this is for binary mass fraction versus the binary eccentricity. And this is the ratio of the acrid for retrograde over the acrid for prograde. Over y parameter space for the binary, the ratio is around 1.6 to 1.7. So it's really easy. And then you notice that in this limit where actually, let's see, so you're now in what's called the Hill slip regime, where actually you're talking about orbit around the smaller object compared to so it's basically a satellite going around a planet. In that case, the ratio is about 2. And he actually quite nicely worked out an explanation of why you would expect that ratio to be around 2 in that limit. Okay? So that's, I think it's actually quite a nice generalization of the Holman and Wiegert criterion.
So when I asked a question about the simulation, simulation, how big the disk is in the setting to the current orbits of the planet?
So let me see. So the problem is, I think my postdoc, she was using some funny units for the, but I think, as you might expect for the retrograde disk, it definitely extends beyond where the current orbit is. What I'm not completely sure is about the prograde disk. So as I said, the prograde disk tend to be smaller compared to the retrograde disk.
This boundary is bigger, for the prograde case, this boundary is bigger or smaller than the test boundary?
That's what I have to check. I think it is actually either smaller or comparable. It might even be smaller. So it then makes it impossible to form that planet in the disk. Which you might expect because you started with a planet.
You are considering different mechanisms that can produce retrograde planets. So would COSI be a candidate?
So COSI would give you something that should be highly inclined in orbit, right?
Or you could be so highly inclined that it's. I think I've seen work where they claim that they can flip orbits.
Yeah.
At the expense of another planet.
The flipping happens for extremely central orbits. So if you flip it, you would have crashed into the star. Most likely.
So that I'm not. So we haven't looked into that possibility, but again, So I think that is, I guess that is a possibility, but there is very likely that problem that you end up crashing into the star. Okay. So lastly, just to advertise something else interesting from the Lick survey. So I don't know, they were looking at 300 and something stars, but it seems to have quite a few interesting systems. So here's one. This is the Lick observation. And so when they were looking at the star at that point, obviously there was a trend with a curvature, so they know that it was probably has a companion. There was no constraint on the period. But there was actually also very clearly what looked like a periodic signal for a planet. This is the data up to this point. So this was the lake data. It turns out that there were older observations of this object, and that was actually some archival data, and which also show periodic shorter period variations. So that was interesting. But the most interesting thing was that they've been observing the system again with the Song telescope, and this is what they saw. So they've now seen it pass through periastron passage, and the orbit is ridiculous. It's 0.93 eccentricity. The periastron distance is 1.31 AU. And if you really believe there's a planet there, it's really bad because the planet orbit has a semi-major axis of about 1 AU. And there's just no way for this to be stable. We've been trying to find stable solution. It's just not even possible. Partly it's because they really know the eccentricity to like 3 digits. So there's no wiggle room there. Okay. So the problem actually, so both the archival data and lake data seems to show consistently similar period. The problem that we are having now is actually the Song data is not consistent. But there are some problems. There are some systematic problems with the data pipeline, apparently. But also because this is the observation over the time when it was changing by 10 kilometers. So it's also maybe not surprising that if you have that large a change in the systematic velocity that you're having trouble discovering the smaller amplitude variation. So that's why I put a question mark. I think I'm still a little bit worried this might not be real. The binary obviously is real, but whether the planet is real or not, I think I'm still worried. Because from stability point of view, I can't find anything stable. So that's the end of what I have. Yep.
For a couple of questions.
Yep.
So I'm kind of curious about the other ones that we talked about. Are they close to stability boundary? The other planets that are not as extreme as this one you showed, are they close to stability boundary?
You mean both of them, or?
You showed 17 or something. Other ones that were much larger period ratios.
Right. The much safer planets, but.
You mean? Oh, no, sorry. You mean the one in this diagram?
So what can you say about generic population? Is there any kind of conclusion you can draw?
I think the one, I'm not completely sure because I haven't actually looked at all of them, even whether they're published dynamical analysis. But I guess the Y separation was you don't expect them to have any problem. But someone may have asked me this before, what is that one? Right, that one might be interesting also. Yeah. The problem with some of these is, of course, they are actually just whatever the observed apparent separation is. So you don't know anything about the binary orbit.
Oh, okay.
Yeah.
It's so wide.
Yeah. Yeah.
But can you say that the planets are around boundary system as often as stable stars at the same time?
So this is, I'm not really sure we know at all because there's been no homogeneous sample for this, I think. Many of these are discovered after the fact, right? Like the HD 59666, it was included in sample. I guess in retrospect, they should have known it was suspected to be a binary system, but they included it in sample and now they know that it really is a binary. So it wasn't selected. So I don't think we have a It was, so I don't think any, as far as I know, there has, so we were discussing over lunch. I thought that someone had tried to do a binary star survey, radial velocity survey before, but I haven't actually seen any results from that, whether they just stopped doing it or what. So I don't know that we really understand the planet fraction in binary star systems. Yep.
You have song data on some of these giants. Is there any hope of astroseismically constraining the obliquity of the primary?
That's what they're trying to do, actually, for some of these stars. So other than the example I showed you at the end, there are other stars that I think including actually maybe 59666, that they're actually observing with song and trying to use astroseismology to constrain the properties. Yeah.
Okay, so we should stop here. And
Okay.
again,
All right. Thank you.